or Trent, are you releasing the project today?
We'll talk about it on Monday because
Monday? Okay.
because the homework's due next Wednesday, and I want to make sure I get through enough content that you guys can do them.
Sounds good. Thank you.
I posted it though, so if you want to read the specification beforehand, you can read it. But we'll go through it together on Monday.
So, with what we currently know, can we get the substantial part done?
Yeah. You can get probably 80% of the project done right now if you really want.
Oh, really? Okay.
Yep. Yeah, for sure.
Get it done. You had an estimate how many hours did you take?
For the project?
Yeah.
That's a good question. I'm not sure actually. It's there's a large coding component of it.
Yeah.
Which depends on how kind of comfortable you are with the coding. But there's also kind of a large report that you have to write with it as well. And so the report, I think would probably take you maybe close to like 5-6 hours to write the report. And then the code maybe around like, depends how comfortable you are, anywhere between like, 6 hours to 20 hours, to get all the results that you need. No, we're talking about Monday because we have homework due next Wednesday and I want to make sure I get through basically everything you need for the homework today. And then Monday, when there's kind of a lull, then that's what we'll talk about.
So it's one starter script and then we just change coefficients. For that?
Exactly. Yeah.
Okay.
Yeah. There's technically two there because that other 20% that you don't know how to do yet we'll cover in a bit. But the basic script should get you 80% of the way there.
Got
Yeah.
it.
Mhm. Okay, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Good, doing good. All right. All right, so today, the plan, I know on Monday I said we talked about the project today, but there is a homework that's due next Wednesday. And I don't want to make it so that, you can't do much of the homework until Monday, because that's too much to kind of cram into a small amount of time. So I'm going to switch it up a little bit. We're going to talk about the project on Monday, and we're going to try to finish up this diffusion modeling with finite volume today, just so that you have kind of more runway for the homework. Okay? Because the gap between Wednesday and Monday is a little bit too large, and I don't want to leave you guys hanging for that on. Okay, so we have that. So today we're going to try to focus on finishing up that code as much as possible. I finally graded your homework 4, so thank you guys for your patience for that. So I did that this afternoon, and the solutions are posted online as well. And so if you go to the weekly page for week 11, you should see a zip folder. And so the zip folder contains all the solutions for the short answer problems, problem 2, which is the hand calculation ones, and it should have the code solutions for problem 3A and 3B as well. Okay, so definitely check that out. I know there were a lot of questions on the last homework, so definitely check that out. And if you have any more questions on the homeworks, just let me know. Okay, all right. And so I think that's all my announcements. So yeah, project we'll talk about on Monday. I did post the project though, and so if you want to take kind of a sneak peek at the problem specifications, I posted a couple of videos in terms of what you can expect in terms of the results, and I posted all the starter code that you need as well. So if you want to take kind of a sneak peek before Monday, definitely you're welcome to do so. And someone asked me before the class, how much of the project can you do right now? Actually, you should be pretty well equipped, and so if you go up to homework 4 and you use the finite difference method, you should be able to do about 80% of the code that's needed for the final project right now. So if you feel comfortable with homework 4 and you want to get started on the project, definitely I would go ahead and get started. In reality, the project is kind of just an upgraded version of problem 3B on the previous homework. You can almost think of it like that. And so if you got problem 3B on the last homework, I would say you're in good shape to start the project whenever you're ready to. All right, so I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right. So last time on Monday, we kind of left off in the middle of an example. So I'm going to scroll up here a little bit. And so you don't have to write this down again because, presumably you wrote it down on Monday. And so I'm just going to pick up kind of where we left off here. Okay. And so on Monday, we started doing this example. And so it was a 1D diffusion example. And so our equation for this is going to be 3 d squared phi dx squared is equal to 2x squared. Okay. on the domain from 0 is less than or equal to x, less than or equal to 1, subject to the following boundary conditions. So we have a Neumann boundary condition of 0 on the left-hand side. We have a Dirichlet boundary condition of 10 on the right-hand side. Okay? And we want to solve this using the finite volume method. Like this, we've done this with finite difference, and so we've done that before. But this time, since we are learning the finite volume method, we're going to use that to solve the problem. Okay, and so what I've drawn kind of visually here on the bottom, let me go ahead and circle it in red. Okay. This is the domain that we're going to be working with. So we have 4 cells. Okay, so I labeled them 1, 2, 3, and 4. They're all equally sized, and so the length of each cell is going to be 0.25 meters, I guess you could say, right? We never really give the units for the x, but you can assume that's meters. Okay. And what I've also marked here is the center or the centroids of each of the cells. Okay, and so I have x1. X1 is right in the middle of cell 1, and so that's going to be at an x coordinate of 0.125. X2, which is in the middle of cell 2, has a centroid located 0.375. Cell 3, its centroid is 0.625, and cell 4, its centroid is 0.875. Okay. So the last thing that we did here was that we listed out the 2 kind of main variables that we need. So we need the diffusion coefficient here, which is -3 in this case, and we have the grid spacing here, which is 1 divided by the number of cells, which is 0.25. All right, and so just like we always do in these types of problems, what we want to do is we want to write out by hand the 4 algebraic equations that will solve for the finite volume solution. Okay. All right, so we're basically going to apply what we learned on Monday. We're going to apply the finite volume method, and we're going to get 1 equation per cell. So, very similar to what we do with finite difference, except now we're working with cells instead of grid points. Okay, so any questions on that? Yeah. Yeah, no, it's a good question. So the K is negative because traditionally, when we're working with the diffusion equation, the diffusion equation, this diffusion term and the source term are normally on the same side of the equation. So I rewrite it differently just because it makes the math a bit easier. But in reality, the true diffusion equation looks like the following. And so we have K, B squared phi, Bx squared plus Q of X is equal to 0. Okay. And so when we include things like the convection term and the unsteady term, diffusion and source are actually on the same side of the equation traditionally. But I write it this way, so I move the diffusion term onto the other side just to make the math a little bit easier once we work out the equations. And so when you actually have like a +3 in front here, so in this example, you can see here we have a +3. That actually means our K is actually negative because there's an additional negative that's out in front. Yeah, no, good question. It's definitely a point that's needed to this. Okay. All right, so let's start writing out the finite volume equations. And just like we did with finite differences, let's start with the interior cells because those are pretty simple to start with. And so remember, the thing about interior cells or interior nodes is that they have neighbors on both sides, right? They have a left neighbor and a right neighbor. And so they can fit our kind of a generic pattern here. And so for finite volumes with just diffusion, our generic pattern is phi r minus 2 pc plus phi sub l is equal to minus delta x squared divided by k times q at xc. Okay. That's a generic pattern that we came up with during the lecture on Monday. Okay. So let's go ahead and apply this to cells 2 and 3, which are our interior cells. Okay, so for cell 2, the right neighbor for cell 2 is cell 3. So we have phi 3 minus 2 phi 2 plus the left neighbor here, which is phi 1 is equal to minus delta x squared. So you have minus 0.25 squared divided by negative k, or divided by k, excuse me, which is negative 3. Okay. Multiplied by q of xc. And so in this particular problem, our q of x is equal to 2x squared. Okay. And so when we plug this in for our equation, we need to include, or we need to plug in the x value for the centroid of that cell. So this can be 2 times xc. And so this can be 2 times x2 squared. All right. And so if we scroll up here, so we can look up and see what the centroid value for x2 is. We can see up here that the x2 value is 0.375. So let's go ahead and plug that into our equation here. So it can be 2 times 0.375 squared. Okay, so that's cell 2. Let's do the same thing for cell 3. So for cell 3, it's going to look very similar. So we have phi 4 minus 2 phi 3 plus phi 2 is equal to minus 0.25 squared. That's dx squared divided by minus 3 times 2 times x3 squared. So x3, if we go back up here, should be 0.625. Yep. Just like that. Okay. So let me go ahead and highlight these just because it's important. So these values, cell centroids. So I think that, that's the part that kind of throws people off with finite volumes, that, when you're plugging in x values and eventually y values for the 2D problems, we have to do those for the cell centroids. Okay. And usually they're a little bit off, right? Because normally, if we have a problem like this and we see that the grid spacing is 0.25, normally when you plug in values for x and y, you plug them in terms of multiples of 0.25. But for finite volumes, they're offset a little bit because they're at the centroids of the cell. All right. Any questions on this? Okay. All right. So that takes care of our interior cells. So now let's do our boundary cells. This part is different for finite volumes because when we're taking the boundary conditions into account, unlike finite differences where our boundary conditions become the equations themselves, for finite volumes, the boundary conditions are going to modify our generic equation. All right, so for these, it's always best to kind of start from the, start from the generic equation and then go from there. Okay. Okay. All right, so our generic equation is minus k times d phi dx evaluated at the right face minus d phi dx evaluated at the left face. Okay. 2 q xc times delta x. So I'm starting here because, the boundary conditions, depending on what they are, they're going to replace these kind of derivative or face values here. Okay. We're going to do something similar in the 2D sense too. Okay. So it's kind of good to kind of get into this practice right now, starting from kind of this generic kind of finite volume equation, basically right after you perform the integrals, and then plug in from there. Okay, so let's start with cell 1. And so cell 1, according to the problem, has a Neumann boundary condition of 0 on the left side. Because from the problem statement, we saw that d phi dx at x equal to 0 is equal to 0. Okay, so let's see how that's going to modify our generic equation here. So in our generic equation, we have minus k times d phi dx on the right face. And so for the right face, we don't have any issues. And so for this, we can plug in our usual linear profile. And so this is going to be phi r minus phi sub c divided by delta x. Okay. This is the same as usual. But for the left face here borders the Neumann boundary, right? And so what we're plugging in for this is d phi dx on the left face. Okay. But according to our boundary condition, d phi dx on the left face is exactly 0. And so for this, we're going to plug in the Neumann boundary condition. Which in this case, conveniently, is just equal to 0. And of course, this is equal to q of xc times delta x. Okay. So let's go ahead and work this out, and then let's go ahead and plug in for the right neighbor and the central cell for this one. Okay. I'm going to go ahead and divide both sides by k by minus k and multiply by delta x. And so on the right-hand side, we're going to have delta x squared divided by minus k q of xc. And then on the left-hand side, our right neighbor here is phi2. Left neighbor, the center cell is going to be phi1. All right, so let's go ahead and fill in for this. And so our equation for cell 1 is going to be 2 times phi1 is equal to minus 0.25 squared, that's delta x squared, divided by k, which is minus 3, times q of xc. And so our Q is 2x squared. It's supposed to be 2 times the centroid for cell 1, which is 0.125 squared. Any questions on how we obtained that that equation there? Okay, so that's cell 1. So now let's do cell 4. That's our other boundary node, or boundary cell, excuse me. And so cell 4, there is a Dirichlet boundary condition on the right. So according to the problem statement, we have phi1 is equal to 10. Okay. And so once again, I'm going to start from the generic equation. So the generic equation is minus k times d phi dx on the right face minus d phi dx on the left face is equal to q of xc delta x. All right, so we're starting from from the same kind of generic starting point here, and we're going to be plugging in for these values here. Okay, so let me go ahead and bring down the minus k. All right, so let's start with the Dirichlet boundary condition. So the Dirichlet boundary conditions on the right face, that means that's going to modify, plug in for this expression here. Okay. Because normally what we plug in for this is phi sub r minus phi sub c divided by delta x. Okay. That's what we normally plug in for this, but we can't do that for cell 4 because cell 4 is on the very right side of the domain. So it doesn't have any right neighbor. Okay. And so we can't do this for this one, but we can incorporate the Dirichlet boundary condition. What we can do is something instead like this. So if we plug in our Dirichlet boundary condition here. And so instead of phi r, we just plug in 10 because 10 is the Dirichlet value on that face. Then what we can do is we can divide by the distance between the cell center and that face. So it's going to be divided by delta x divided by 2. Okay. Our other face value is still going to be the same. So d phi dx at xl is still going to be phi sub c minus phi sub l divided by delta x. Okay. And this all going to be equal to q at xc times delta x. Okay, so let's go ahead and plug in all the numbers for this. So for cell 4, I'm going to go ahead and multiply both sides by delta x, divide by minus k. And so on the left-hand side here, we have 10 minus phi sub c. Phi sub c is just phi 4 minus phi sub c, phi 4 minus phi sub l. The left neighbor for cell 4 is cell 3. Okay. This is equal to delta x squared divided by minus k, q of xc. Oh, excuse me, I forgot to bring up the 2 here. And so this should be 2 times 10 and 2 times phi4. Sorry about that. So those first 2 terms there have a 2 multiplied by them because of the delta x divided by 2 in the denominator. Okay. This should be a plus phi3. Sorry, a couple mistakes in that line. So the phi3 should be positive, and the first 2 terms should be should have a 2. Okay, now it's looking right. Sorry about that. All right, so what I'm going to do is, because this 2 times 10 here, it does not have any phi component to it, I'm going to go ahead and move that to the other side of the equation. Okay. And I'm going to simplify the left-hand side. And so on the left-hand side, we have a minus 3 phi sub 4 plus phi sub 3. Okay. This is equal to, so let's go ahead and plug in for delta x and k. And so we have a 0.25 squared divided by minus 3 multiplied by 2 times x4. So x4 is 0.875 squared. And I'm going to subtract 20 because that came from that term. And so that right there gives us our equation for cell 4. Okay. Any questions on this? All right, and so if we combine this together with our equations for cell 2 and 3, those are our interior cells. That's the kind of the first thing we did in this example. We combine this together with cell 1, which is our Neumann cell. We have our 4 equations here for our 4 cells. So we're basically done. Okay. Remember, when you're doing these finite volume problems by hand, you want to really be careful with the boundary conditions, because just like you saw right now, it's very easy to kind of mess up the signs for these equations. It's very easy to kind of not take into account the boundary conditions correctly as well. So you want to be careful with these steps. I know it's a pain to go from this kind of generic step here, but for some cases it's going to be really important, especially when we get to 2D, because in 2D it's very, very easy to mess up the sign. And so you want to make sure that you're being careful and you're doing all this kind of diligently. Okay. And so before we move on to 2D stuff, I do want to take a look at the MATLAB code. Okay. So let me go ahead and switch to my computer screen here. I believe, yeah. Okay, so this is the 1D code right here. Okay. So this is posted on Canvas. And I was telling a few people earlier that I'm posting these example codes for you guys to use. And a lot of times when I give you guys a MATLAB problem on the homeworks, they're actually quite similar to these example codes. So a lot of times say like you're doing like problem 3A on the homework, look and see what's the example code that kind of most closely matches this, and then kind of just tweak it a little bit. So that might be a little bit easier, because I know I give you guys the starter code for the homeworks, but it might be easier to go based off the example codes from the class and then modify that to match whatever the problem is on homework. That might be a little bit easier to do than going from the starter code. Okay. Granted, if you do go from the starter code, you're going to learn more because you're coding more of it yourself. But if you're really stuck, definitely look at the example codes from the class and then use that as a reference for you. Same thing for the project too. And so from the project, I can tell you with certainty that we've covered, at least one example code in the class that'll help you out tremendously for the project. So, definitely use that to your advantage. Okay. So this is our code here, and there's not that much to highlight here because a lot of it is fairly standard in terms of 1D problems, but there are kind of a few things I want to highlight. All right, so first of all, I want to highlight this line of code right here. So, we're in section 1. And so remember, section 1 of the code is always going to be your kind of your setup phase where you kind of define all your variables. In particular, I want to draw your attention to this variable right here, which is x sub c. Okay. And so if you read the description of this variable, you can see that what it is that it's the location of all the cell centers. Okay. Remember, when you're doing finite volumes, the locations of the cell centers become really important. And they're especially used when you need to plug in for X or Y into the equation. Okay. So keeping a variable here that keeps track of the cell centers is very important. And you can see here that, the code here is a little bit complicated, but this is just to make sure that we offset appropriately for the, for each cell center. Okay. Because if you look at the last problem, our cell center started at 0.125, which was half of the grid spacing. So that's kind of why we start for this one here. Okay. And then we end on, the length of the domain minus 1/2 the grid spacing, which is this one right here. Okay. And so if you plug in, x is equal to 4 or n is equal to 4 here, you should see, the cell center coordinates be exactly what we covered in the example that we just did. Okay. And then besides that, we have, our left-hand side matrix, our right-hand side vector. We have our diffusion coefficient. I think what I did in this code is that, because, we kind of have a double negative on the right-hand side, I just canceled that out. And so that's why you see a k is equal to +3 here. But, if you wanted to be a purist, this would be actually -3. But I think what I did, I just kind of canceled out some of the negatives. Okay, and so now we get to kind of the meat and potatoes of this code. And so this is, where most of the work is happening. Okay. And just like we did with finite differences, the way that you can interpret this loop is that, we're building up our system of equations. We're building up our matrix set of equations. We're building up one row at a time. Okay. And so when you see a loop here, okay, so we're looping over all the cells, each iteration of the loop, we're going to basically define an equation in our matrix. Okay. And so you can see here the biggest kind of structure that you see inside this loop is that we have this if, else, okay. And these are going to be for our 3 different conditions that we have. And so let's look at the else statement first, because that's kind of the easiest one to look at. That's if we were in an interior cell. Okay. So if we're in an interior cell, we have all of the kind of generic coefficients here. So we have 1, 1 minus 2, and then our right-hand side is equal to this. And so we have dx squared divided by k times q sub c, q at xc. Okay, so we have 2 times xc squared. Okay. And so that's going to work for all of the cells that aren't on the boundaries. So for the cells that are on the boundaries, and so let's say that we're on cell 1, we need to apply a Neumann boundary condition in this case. Okay. And so you can see here that that's going to change the coefficient values. So instead of -2 and 1, 1. We just have -1 and 1. Okay. And then our right-hand side is still the same. And then for this else if statement here, this is for the rightmost cell. And so for this, we have a Dirichlet boundary. And so again, going off our hand calculations, that means our coefficients are going to be -3 and 1. Okay. So for the phi sub c and phi sub l. And then this is going to be on the right-hand side. So we have our typical source term here. And then we also have this -20. Which comes directly from the Dirichlet boundary condition. Okay. Okay, so let me go ahead and run this code so you can see what it looks like. And you can see here that we kind of match the exact solution really well. So we have a little bit of errors here. I can see a little bit of blue peeking out there, but with 40 cells, this kind of matches the exact solution, right on the dot. Okay. All right. And so, yeah, question.
I saw in the beginning variable section, I saw x. Is that just for the plotting?
Yes, the x is just for the plotting. Yeah. Yeah. It's also for the, well, I guess you don't need it for the grid spacing, but yeah, this x right here is just for the plotting. Oh, I didn't even use it for the plotting. So actually this x here is unused. Actually. So yeah, so when you're doing finite volumes, you only need the cell center value, so you don't need x. All right, and so, the big difference here, of course, is that, when we have boundary conditions, they don't get their own equation. The boundary conditions just modify our generic equation. And that's the biggest difference between finite difference and finite volumes. Right? And so some people like this. And so, if you remember from finite differences, we had kind of one loop that was for all the interior nodes, and we had either separate loops or separate lines of code for the boundary conditions. With finite volumes, we can kind of package it all together into one loop, and so it kind of paints a cleaner picture. It's a cleaner kind of code because it's all in one loop. And so, it's a matter of personal preference, kind of what you prefer. Some people like this, some people like finite differences, but it's just whatever you feel kind of. Okay, any questions on this code here? Okay. All right, so remember this code is posted for you, so definitely take a look, especially when you're working on problem 3A of the homework. So let me go ahead and bring it back to the notes. Let's talk about 2D finite volumes. Okay. So now that we've done 1D diffusion with finite volumes, we're ready to start doing 2D. Okay? So let's start out with the generic kind of 2D diffusion equation, and then we'll apply finite volumes to them. And I'm going to write it in vector form just because it's going to make applying the integration rules a little bit easier. And so in vector form, we have a minus k times the divergence of the gradient of phi is equal to q of xy. Okay. So this is the equation in vector form. All right, and just like we did in 1D, we're going to take our generic partial differential equation here, and we're going to integrate it over the area of a cell. So we have, I'm going to factor out a minus k just because it's a constant. Okay. And so in 2D, when we're integrating over a cell, that means we're going to do a double integral. So on the left-hand side, we have a minus k times the double integral of the divergence of the gradient of phi dA. And on the right-hand side, we have the double integral of our source term q of xy dA. All right. So the main step that we're going to do here is that we're saying that this integral here on the left is very difficult to compute because we have a divergence and a gradient in there. And so what we're going to do is we're going to convert this to a line integral using the divergence theorem. All right. And so from this, we have minus k. We have a line integral around the boundary of the cell or the edge of the cell of gradient of phi dot product with n ds is equal to u of xy d. All right, I'm gonna box this for now because this equation we're going to be working with over the next 10-15 minutes. And so This is kind of a good place to stop. In particular, we're going to be working on the left-hand side of this equation. And so this line integral here is going to be the focus of our attention. So what this is that this is a line integral. It's a line integral that goes around the boundary of our cell. Let me draw it visually here just so that you can see. And so in 2D, we are going to have square cells now. So that is our cell. And when I say that we are performing a line integral, that means we're basically going to be traversing around the outside of the cell. And so the arrows indicate the path of our integration. So, it doesn't really matter where you start. And so, here I started in the top left corner, but we're going to integrate, from, going around the top edge, the right edge, the bottom edge, and the left edge. Okay. In fact, because we have some sharp corners for integration path here, it's going to make our lives easier to break up the integration into 4 different integrals. And so on the top, I'll label that with N for the north face. For the right side, I'm going to label that with an E for the east face. The bottom side is going to be the south face. And the left side is going to be the west face. Okay. So what I'm going to do, so let's break up. So let's break up the line integral into 4 separate integrals, with each integral covers each face of the cell. Okay. And so our integral here, I'm going to ignore the minus k for now. And so the minus k will bring back a bit later. But I'm just going to focus on this integral right now. So we have line integral of gradient to phi dot n hat. Okay. Well, in case I didn't mention it, so the reason I'm using that circle on the integral sign, that means that our integration is going to be on a complete path or a closed path. Okay, so our starting and ending point is the same. Okay, so let's break this up into 4 integrals. So we have an integral north face correlation with the jacket company. Then we have an integral on the east face. Integral on the south face. Fit it. So we'll have an integral on the west face. Okay. So you're probably looking at this and you're thinking, that doesn't look easier. That looks worse. So you took one integral and turned it into 4, right? One integral is bad enough. So 4 integrals is 4 times as worse. Right? I know it looks bad, but trust me that this is kind of the way to do it. Okay. once we start plugging in for the gradients and for the normal vectors, you know, it'll start to move a little bit better. Okay. But let me pause here for questions. So are there any questions on this so far? Okay. All right, so now we've kind of broken up our line integral. So the integration part is okay for now. So I'm going to go ahead and leave that alone. What I want to focus on next is the integrand. So in each integrand here, we have this quantity gradient of phi dot product with n. Okay, so it's a dot product quantity. So let's kind of break this down into each component. We're going to go over the integrand. First, we have gradient of phi. And so the gradient of phi, if you're not familiar with the gradient operator, it's basically going to be an expanded derivative. So we're going to take partial derivatives of phi in each of the x and y directions, and we're going to store that into a vector. Okay, so the gradient of phi is a two-component vector in 2D. So we have partial phi partial x and partial phi partial y. Okay. So gradient derivative in each. So that's pretty, straightforward. The normal vector is interesting because the normal vector, what it is that it's called an outward facing unit vector. N hat and so basically what it is that it's a vector that points in the outer direction on whatever face that we're on. Okay. And so, hopefully now you're starting to see kind of the logic of kind of breaking this up. Because if you look at this square, okay, and if we were to draw an outward unit normal on each edge of the square, and so if you look at the arrows that I drew on the north edge, on the east edge, the south edge, and the west edge, you can see that they're all pointing different directions. Okay? So the direction, this vector, direction of this vector changes for each edge of the cell. Okay? And we can actually write these down. And so for the north edge, the normal vector looks like this. Pointing straight up. And so if we were to put this in mathematical terms, this would be 0, 1. For the east edge, the normal vector is going to be pointing to the right. So the vector representation for that is going to be 1, 0. For the south edge, our unit normal vector is going to be pointed straight down. And so that means its numerical representation is going to be 0, -1. Finally, for the west edge, our normal vector here points to the left. And so that means our numerical value for this could be -1, So each face here has a different normal vector. So that's kind of why we split it up. So, this makes it easy. So as long as we stay on one particular edge, so as long as we stay on the north edge, that normal vector is going to be the same. So we don't have to worry about switching it up mid-integral. Okay. All right. So now that we know what the gradient of phi looks like, so now that we know what the normal vector looks like, in order to plug it into this equation up here, we have to take the dot product between these two quantities. Okay. And this one, and this one. But luckily for us, our normal vectors here have a lot of zeros. Okay? So those zeros are going to cancel out when we do the dot product. So when we perform the dot product on each edge, they look like the following. So for the north face, okay, gradient of phi dot product with n is equal to, okay, we're going to have partial phi partial x comma partial phi partial y dot product with the vector 0 comma 1. Okay, so that 0 is going to cancel out the partial phi partial x, and so all we're left with is partial phi partial y. Okay. For the east face, we have gradient of phi dot product with n. Okay. Once again, we're going to have a 0 that's going to cancel out. And so we end up with partial phi partial y, x for that one. I'm going to fill in the other ones fairly quickly. So for the south, we get a minus partial phi partial y. And for the west, you get a minus partial phi partial x. Okay. Right. So now that we have this, let's go ahead and plug these back into the integral. And so we plug this back into the integral that we get our line integral of gradient of phi dot product with n ds. Okay. We broke this up into 4 integrals, and so we have an integral on the north face of partial phi partial y dx plus integral over the east face of partial phi partial x dy plus we have it, right? Yeah. And then integral minus integral on the south face. Partial phi, partial y, dx, minus integral on the west face, partial phi, partial x, dy. Okay. All right, so now we have our 4 integrals. They're a lot simpler than they were before, okay? But they're still integrals here. Okay? So let's use a trick here. Let's use an integration trick because we don't actually like performing integrals, so we like to just use tricks instead. Okay? So let's use the trapezoidal rule to evaluate these integrals. Okay? Okay, so remember the trapezoidal rule, what we do is we evaluate these integrals, we evaluate the integrand at the centroid, and then we multiply by the length of the integration domain. Okay, so starting on the north face, we have partial phi partial y. Evaluate the centroid of the north face times delta x plus partial phi, partial x. Evaluate the east face, delta y, minus partial phi, partial y on south face, delta x, minus partial phi, partial x on the west face, delta y. Okay. Let me go ahead and box this for now, just because this is kind of a good time to pause. Any questions on how we got to this point here? Okay. And so now we're at this part where we have to evaluate these kind of derivative components on each face of the cell. Okay. And so if you remember, we had this issue in 1D as well. And so in 1D, we had these derivative quantities that we had to evaluate on each edge of the cell. Okay. And remember what we did at this point in 1D. In 1D, what we used was basically a forward difference scheme to evaluate these face derivative quantities. Okay, so we're going to do the exact same thing here. So let me go ahead and draw a diagram for you just to kind of make it a bit more clear. Okay. All right, and so we have our center cell, so phi sub c. But our phi sub c is going to have neighbors, and so we're going to have a neighbor to the north. So we'll call that phi sub n. We have a neighbor to the south, phi sub s. We have a neighbor to the east, phi sub e. We have a neighbor to the west, phi sub w. Okay. All right, so let's use all these neighboring cells and let's come up with expressions for each of those derivative quantities. Okay, so let's start with the north face. Okay. And so on the north face, we have partial phi, partial y, evaluated on the north face, okay, or north edge. And so if we use a forward difference here, this is going to be phi sub n minus phi sub c divided by delta y. On the east face, we have partial phi, partial x. On the east face, this is going to be phi sub e minus phi sub c divided by delta x. Okay. On the south face, we have partial phi, partial y. South direction, that's going to be phi sub c minus phi sub s divided by delta y. And on the west face here, we have partial phi, partial x. West face, phi sub c minus phi sub w divided by delta x. Okay. So let's take all these and let's plug them into our expression above, okay? And I'm going to do one big assumption here, which is, for this class, it's a very reasonable assumption. So let's assume that our grid spacing is equal in both directions. So we have delta x is equal to delta y. Right, and so that's going to be really key because when we plug this in, you can see that here we have a delta y on the bottom for the north term, okay? And that's going to be multiplied by delta x over here. So that delta x there came out of the trapezoidal rule, okay? But if we assume that these two are equal, so delta x and delta y are the same, then these two are just going to cancel out. Okay? Okay. So let's go ahead and plug those in. And so if we plug in for this, then what we get is phi sub n minus phi sub c plus phi sub e minus phi sub c minus phi sub c minus phi sub s minus phi sub c minus phi sub w. Okay. Let's go ahead and simplify this. And so you can see we have a bunch of phi sub c terms here. And so with that, we have phi sub n plus phi sub e plus phi sub s plus phi sub w minus 4 phi sub c. Okay. All right, so we're just about done. And so the last thing is just to kind of plug this all the way back in. And so if you remember, this integral that we're working on actually belonged to this integral right here. Okay? And so we have minus k, and then that's going to be equal to the right-hand side here, which is double integral of u xy dA. Okay. Okay. And so our 2D diffusion equation for finite volumes so our 2D diffusion equation using finite volumes looks like the following. So we have a minus k times this quantity that we just derived. So we have phi sub n plus phi sub e plus phi sub s plus phi sub w minus 4 phi sub c. Okay. This is all equal to the right-hand side. And so the right-hand side is just going to be the source term, or in other words, the double integral of the source term, dA, okay? Okay. And so just like we always do, we have an integral here. We can't really simplify it anymore. We can't apply any divergence theorem because we don't know what Q is. And so we're going to use our normal trick. So our normal trick is that, we don't want to perform this integral. So let's just use trapezoidal. So if we apply trapezoidal rule, we're going to evaluate our integrand at the centroid of the integration domain. So this can be q of xc comma yc. We're going to multiply by the area of the domain, which is delta x, delta y. Okay, and so let's go ahead and bring down the other stuff. So we have a minus k. You can divide by minus k if you want. That's kind of a traditional thing, but I'll go ahead and leave it here for now. So this equation right here This equation right here is our 2D diffusion equation with finite volumes for the interior cells. All right, any questions on this? Okay. All right, so let me pause here for a second because you know, we didn't get nearly as far today as I thought we did. Kind of, I guess I rambled a lot today. And so what I'm going to do is I'm going to push the deadline for the homework back. And so instead of being due next Wednesday, it'll be due the following Monday. So you guys will have an extra 5 days for that because I can't reasonably say that after today you can do the homeworks. You should be able to do the A parts of the homework, so you should be able to do 2A and 3A. But for 2B and 3B, let's finish up this discussion on Monday, along with the final project discussion, and then after next Monday, you should be able to do homework. So I'll put an announcement out today that the next homework can be pushed back until the following Monday. Okay. Okay. All right, and so, but before we head out today, we do have 10 more minutes. Let's go ahead and talk about boundary conditions in 2D. Okay. So just like in the 1D case, you know, our when we apply boundary conditions to 2D finite volumes, the boundary conditions are not going to become their own equations. The boundary conditions are going to modify our generic equation, which we have above. Okay? And so just like in 1D, I recommend that you start from a point, you know, before we start to apply the forward difference. Okay? So if you recall, you know, that point was this. So we have a minus k, and when you plug in for all the face integrals, so we have partial phi y on the north face multiplied by delta x plus partial phi partial x on the east face times delta y minus partial phi partial y on the south face partial delta x minus partial phi partial x on the west face delta. Okay. And so when you're applying boundary conditions, you know, especially when you're first starting out, especially when you are kind of doing these kinds of problems for the first time, I really recommend that you start from this point here, because, you know, what we have here is we have a situation where we've kind of separated out really nicely. So each term in this expression, each term in this expression represents one of the integrals that we started with. Okay? Remember, when we started this kind of journey in 2D, we had 4 integrals that we had to evaluate, right? So an integral on the north, on the east, on the south, and on the west. Okay, that's going to make things easier conceptually when you're applying boundary conditions, because basically what a boundary condition is going to do, it's going to replace one of those base integrals. And so starting from a point where you can kind of clearly see, each of the terms here, so we have 4 terms here, where each of these represent one of those face integrals, it makes it easy to kind of replace one when you're writing out your equations. Okay, so I'm gonna do a couple examples. I think it's kind of best illustrated from examples. Let's say that we have a Dirichlet boundary condition on the west face. We have a situation like this. So we have a cell that's going to be bordering on the left boundary of the entire domain. And so it doesn't have a left or west neighbor. Okay, so let's say that we have phi sub c here. We have a north neighbor, phi sub n, south neighbor, phi sub s, and then east neighbor, phi sub e. Okay. But on the left side of the cell, we have phi is equal to phi naught. So in other words, we have a Dirichlet boundary condition on the left side. So what this is going to do is that's going to modify our west integral term. So we have partial phi, partial x on the west face. Okay. Normally what we do is we do phi sub c minus phi sub w divided by delta x. Okay. So that's what we did above there. We can't do that here. We don't have any west neighbor. So what we're going to do instead of west neighbor, we're going to keep phi sub c there. But instead, what we're going to do is we're going to plug in the Dirichlet value here. So we're going to have a phi naught and divide by the distance between phi sub c and the boundary. So it's going to be divided by delta x divided by 2. Okay. We're gonna go ahead and plug this in, and so this go up here, but all of the other integrals are going to stay the same. So since we have neighbors on other sides, all the other integrals will stay the same. All right, and so if we do that, so just in the interest of time, I'm going to go ahead and skip to the results. And so if you plug kind of everything in, we end up with the following. So we have a minus k times phi sub e plus phi sub n plus phi sub s, so those are all the neighbors. Minus 5 phi sub c. Okay. On the outside here, we're gonna have an extra term for the Dirichlet boundary condition, so it's gonna be a minus 2k times phi naught equal to q at xc yc delta squared. So of course, since this term right here, there's no unknown phi associated to it. So now I know we have the Dirichlet boundary condition. We move this to the right-hand side because that value is known. And then that becomes our equation for that cell. Okay. And so we still have contributions from the east, north, and the south neighbors because those exist. But instead of the west neighbor, we replace that integral with an expression with the boundary condition. Okay. Any questions on this? Okay, all right, so we'll pick this up on Monday. We'll finish up these lecture notes then. Remember homework 5, I'm going to push the due date back for that until the following Monday. Just so you guys have some extra time, because I don't want to rush you guys on finishing the homework within 2 days. That probably means we're going to push back the midterm a bit too. So I'll make an announcement. I'll kind of re-forward the schedule and then let you guys. Okay. All right. So thank you guys for coming today. Hope you guys enjoy the rest of your evening, and I will see you next week. You guys have a good weekend. You guys have a good weekend. Abraham.